We're going to do a brand new exercise for us. We decided that, well, first of all, I don't know if you guys remember, last year we got teachers for 1 day. The year before that we did 1 day. The year before that we did half a day. And the year before that we just did like 1 session in the afternoon or something like that. So they have slowly increased the amount of effort that they're throwing onto us. This year we looked at this and 5 days, what are we going to do for 5.5 days? We only, we have a certain number of workshops and such. So we created a bunch of new things for you this year. One of them being that reverse asteroids exercise that we did yesterday. It was something that we hadn't used before in teacher workshops. Another thing that we created, well, this one arose on the New Jersey Turnpike because Bonnie and actually my mom and I were up at the Intrepid Museum in New York City for an astronaut event last fall. And we were thinking about, well, what can we do that's something different for this? And we were thinking about trying to use data in the classroom, okay? And in astronomy, there's a lot of push to say, hey, can you use astronomy data in the classroom? We've got the archive of the Hubble images at Space Telescope. And so we want to work with the archive group and see, can they, and the archive group said, yes, we'd love to see teachers coming to the archive, pulling data out, real Hubble data out of the archive, and use it in the classroom. The major problem with that is it's very specialized measurements and scientific formats, okay? For some things, if we're doing spectroscopy and the units that we're using and the ideas of what we're measuring and this colors, B minus V colors and other things, the variety of things that we're using are specialized measurements. That's a little difficult, but you could probably get past that. The other thing is the data formats. We have something called Flexible Image Transport System, which is written by astronomers for astronomers and would not be loved by anybody else. There aren't JPEG images that we produce in our things. And so there's a significant barrier to getting real data into the classroom. And so Bonnie and I were trying to brainstorm on, well, what can we do where we get real astronomy data into the classroom in a way that can be utilized? Now, we had done the mixed up solar system. How many people did the mixed up solar system thing with us? I guess it was last year? We did?
Yeah, last year.
Was it last year? One of them. We do that a lot, okay? Where we gave you the information on 16 objects in the solar system, and you plotted them, and you were able to organize the solar system, and in your own way discover that bullseye diagram that I showed you there, okay? So we said to ourselves, well, wait a minute, what about stars, okay? Plotting of constellations would be something that would be relatively simple to do, right? You're just plotting the points of stars, but it has a little twist because it's astronomical coordinates, and so it would give kids practice in doing plotting, but you have a bit of a twist to it that would help them understand what you're looking at in the sky, and the end result would be a recognizable pattern that they will have seen in pictures and in books and in constellation drawings and such. So we said, all right, cool, let's try and develop that. Of course, we didn't actually do anything for quite a while until these workshops started coming up, and then we sort of crammed and put together, and our wonderful Joey back there helped get all the data and such together and all the plotting and working together, and so we came up with this charting the stars idea. So, here is that picture of the Orion constellation that I've shown you before. We have this wonderful X pattern here that makes it recognizable, right? So what we want to be able to do is to give you the astronomical coordinates for all these stars. You have them sitting in front of you, okay? Joey handed out this table. May I borrow this for a second? So this is your data table. There are 3 constellations there. We'll take them one at a time, all right, and work through them. Now, so what makes this challenging? If you're just plotting 7 points, well, the challenging part is that you've got to use astronomical coordinates. You're not using simple X and Y. Okay, we're not giving you X and Y. We're giving you right ascension and declination. Okay, that's how astronomers plot things on the sky. All right, right ascension is abbreviated as RA, and it would be your longitude in the sky. Okay, Latitude goes up and down, longitude goes left, right, okay? Remember? All right. Now, it is measured in a funky way. It is not in degrees, as you would normally expect, as longitude is on Earth. It is in hours, minutes, and seconds, where there are 24 hours in a circle, 60 minutes in an hour, and 60 seconds in a minute. Okay? And it derives from when you're doing timing of positional measurements. So, let me help you understand why right ascension is a reasonable thing to do. It's not a crazy thing. When we were doing positional astronomy, as you noted, finding that Sirius was moving across the sky, you had to measure those positions really precisely. So what they would do, especially before the invention of the telescope, is they would time when that point crosses the north-south line. Matter of fact, Tycho Brahe, the greatest observer pre-telescope, his greatest instrument was perfectly aligned along the north-south line. And then he would sight along that north-south line and time exactly when that star or that planet or whatever it is crossed the north-south line. So he could measure an angle above the horizon and a time. So angle above the horizon would be in degrees, the left-right would be in time. All right? So he would be measuring the time and the angle. Hence, the right ascension, the left-right, is measured in hours, minutes, and seconds. All right? And hence why we get 24 hours in a circle, 60 minutes in an hour, 60 seconds in a minute. Okay? Because he actually didn't measure an angle, he measured a time. Okay? So, declination, as I've just indicated, would be the latitude in the sky. It's usually abbreviated as dec, okay? Go back. The full thing is declination. We just go RA and dec. And for some reason, RA is usually capitalized. Dec is usually lowercase. I don't know why. It's just the way it has come down to us. So this is the latitude. This is the normal degrees, arc minutes, and arc seconds. Okay? Because we use hours, minutes, seconds, and we use degrees, minutes, seconds, I will try, and I will not succeed, but I will try to say arc minutes and arc seconds when I mean those, okay? All right, so 60 degrees in a circle, 60 arc minutes in a degree, 60 arc seconds in a minute, in an arc minute, okay? Like latitudes on Earth, they are measured relative to the celestial equator. So we go from 0 degrees at the equator to 90 degrees north. Does anybody know what star is near 90 degrees north? The North Star name is Polaris. Okay? Polaris is the North Star. It's not exactly at 90 degrees north. It's at like 89.5 or something like that degrees north. It's just close enough that it always is in the north part of the sky. And then we go to 0 to minus 90 degrees at the South Pole. Anybody know the star at the South Pole? There isn't a star at the South Pole. That's a trick question, sorry. There are some stars near the South Pole. There actually isn't one particular bright star near the South Pole. I'm sure if we look faint enough, there would be a star near the South, very near the South Pole. But there is no bright star near, so there's not a South Polar star. Oh, and by the way, for trivia, the North Star is only the North Star for now. The North Pole of Earth librates because Earth's rotation actually wobbles a little bit. So about 6,000 years ago, Vega was the North Star and not Polaris. Okay, so Polaris, the name Polaris is going to be out of date in a couple thousand years as it goes away from the North Pole. But you and I won't be around to worry about that. Other later astronomers will have to deal with that. But back to what we're doing. 90 degrees north, 90 degrees, minus 90 degrees south. Okay? Great. So, here's an example. The star Rigel, its right ascension is 5 hours, 14 minutes, 32.2 seconds. Its declination would be minus 8 degrees, 12 arc minutes, 6 arc seconds. All right, this is what you will find. I hope that's what's printed on your sheet for the star Rigel. All right, so here's your plotting challenge. We have to take these hours, minutes, seconds, and these degrees, minutes, seconds, and convert it to some sort of linear measure, because those aren't linear. Remember that it's not decimal, it's in units of 60 for a lot of these things. So 50 isn't halfway, 30 is halfway, right? Something, just a small little tweak on things like that, okay? So let's take a look at the Orion data, all right? So in the blue shirt here, can you tell me what is the smallest right ascension you see in that data? Which star? Rigel, okay, that's at 514, right? Okay, and over here in the purple shirt, what's the largest right ascension? Betelgeuse. Okay, Betelgeuse is at 555. Okay, so we go from 514 to 555 in right ascension. All right, same thing for declination. How about you? What's the smallest declination we see?
I would go with negatives or close to 0.
I would go with negatives as being lower than 0.
Rigel.
Okay, so Rigel is at minus 812. No, you're right.
Yeah.
I don't know how to pronounce that, whether that's safe or saif or saif or whatever. Anybody speak?
No, but NPR says SIAF, so.
NPR says SIAF. I will go with NPR. Okay, they know more than these. They would research these things more than an astronomer would. Okay, so where did you hear that on NPR?
They were doing something, I don't know, a couple of months ago, about actually this constellation, the Orion, and they were going over all the different names, which I didn't know. And
it's fascinating that somebody actually has heard of the star Saiph, because Rigel and Betelgeuse, and sometimes Bellatrix, people know that from the Harry Potter film, and books and films. But Saiph, great. Okay, so Saiph is at minus 940. Okay, around. All right, and what is the largest one? Who haven't we talked to? Over here in the pink. What's the largest declination?
Betelgeuse.
Betelgeuse at plus 724. Okay, you will often find astronomers saying plus 724 and minus 724 for declinations and such, just to make sure that we say the plus, we don't just imply the plus. Okay. All right, so always very good to recognize your boundaries, right? What your highs and what your lows, and the min and the max, because we now have to plot them. John, have we got Joey? We're going to hand out some plotting thing. Okay, so the first thing we do is we gave you a plot that you can put in. You notice we've got 5 squares on the x-axis. We have 3, 6, 7 on the y-axis. The first thing we have to do is label our axes. We just talked through the min and max type things. So here are the axis labels that I came up with in order to make it easy. All right, so we basically go from about 5 hours in right ascension to about 6 hours in right ascension. We go from making it easy, we go from minus 12 in declination to plus 9 in declination. All right, because we had about minus 10 to plus 8. And so making this easy worked with that. Now, here's the interesting point, all right? Recognize that you're dividing 60 minutes into 5 increments, which means this is 512, 524, 536, and 548. All right? Helps to have those down there when you are doing the plotting. All right? And so now it is your challenge to do this plot for the stars in Orion.
Yeah, I do this.
This is 40 times. So the axis, the y-axis.
If we start our graphs at zero,
Degrees of the rise.
very few things
Yes,
can't start
up
at
and
zero.
down.
Right,
The x-axis
right.
is based left and right based on the celestial sphere. So if we take the latitude and longitude of Earth and project it out into the sky, there'll be a celestial equator, there'll be a celestial north pole, and a celestial south pole.
And it's just moving the graph
So
up.
going up and down on this
Put the
equator
zero in here.
is up is the up and down in the sky. That's declination. And then going around the circle is right ascension.
But what we're doing here is a coordinate plane, it's graph.
They're not exactly the same thing.
If it was a coordinate plane, it would start with zeros, and then all of those things would be below.
So what's the problem?
Right, it's just a, yeah. I just gave you an unlabeled plot so we could label it how we needed to.
In our math world, we always start at 0, 0, so we're like,
Oh,
the
okay,
five, you know what I
right.
mean? Like, we're just,
Both
and that's how
are-
we teach our kids too.
Okay.
That's what our conversation, so we would.
Great,
she
great, no, that's what I'm
doesn't
trying, I'm trying to
science,
understand what the
correct.
conversation is.
Yeah,
so.
she doesn't, like, we would have shifted this down and put like 0 here probably, and then 5, 1, and then down below it has the negative.
Okay.
Like, we don't have to do the same scale.
If I was to ask my freshmen to graph this data, they would, their minds would explode.
Cool.
Because they want to start at one graph at zero.
Yeah.
Okay, so there need to be strong lines at 0, 0 for them to work off of. And then they can go below that, or they can go to the left of that as necessary. But they need the axes drawn across the 0, 0.
Because that's all they've ever done.
Yeah.
All right.
I've actually stopped having them label the axes themselves because it's
It
never
takes
what-
too long.
but Yeah, then we have to go back and explain that,
Yeah.
okay, we don't have to do it this way.
Okay, cool.
Do you think you could take one little mini lesson and show them like a graph with 0, 0 and then like take a little picture of a piece of the graph and have them like label and pull it out and understand it?
I could, but for the amount of graphing we do in biology, I'm
Oh,
not sure that a
You
whole
don't have
lesson
that
would.
time.
In bio,
Yeah,
you
you
know,
don't
part of
have
it.
that
You're right. Alright, maybe my sword is backwards. That's right.
So they're just like, this is We're looking at it, we're looking at it as if Orion is.
I thought I did it wrong.
This is really.
The latitude versus longitude being backwards.
I was going to just make a note of those.
This isn't.
That's the point of this.
Okay.
Okay.
Right.
Yes, sure.
Right.
The coordinates is something measuring time. So that's fine. Like I said, this is relative to some little time in the sky. Okay. This is at 5 hours and 34 minutes. 13 seconds. Okay. Relative to the, like we have a third one on Earth. The time versus
Yeah, because.
so our longitude is due west of that time. Right?
Oh,
So the sky, less than how many hours away from that? Yeah, there will be a 0 1. And generally, everything is easier to measure as different measurements. Right, so this star, this star is 4 hours and 12 minutes. And then we find, okay, well, this star here is 0 point, and then we'll generally, you're not able to consider one of the guys say, once you define here are all the primary stars, you get one primary star, and then there's a differential one, when
the 3-year goes.
Is there a way that if I'm using these numbers and I'm outside of the stars, how do I translate this?
Okay. So generally what you do with coordinates is you're going to use a star chart and you'll recognize a pattern and then you'll start from there in terms of figuring out if you're running a telescope, you have to orient your telescope. And so you can either look at Polaris, which is close to, for low precision accuracy, you look at Polaris, lock that in as 90 degrees, then you find another star that has a known position, you lock that in, and basically measuring 2 stars by pointing your telescope exactly at 2 stars, and using that, you then orient your telescope. Now, generally expensive telescopes are in concrete pier, and they're mounted and oriented and adjusted really finely once, and then they don't have to be readjusted.
So this projection of is that done like percentages, like absolutely? This is where
You define your standards, okay? So generally what they would do is they would define the folks who set this stuff up 1,000 years ago would define here's these stars have these positions, and generally if you have enough stars across the sky you can always say, okay, well there's one star that I know its position, and there are a couple stars in the night sky that I know the position, and I can lock onto those and then measure everything relative to those. So a lot of what we do in positional astronomy is relative measurements. Okay. All right, let me move on here.
All right, folks, I think we got enough chatter going that says, hey, we're basically done. Yes, question?
Okay, well, request.
Request. Okay.
Because I can see myself using this for my biology students, because
Okay.
when they come to me, they always ask, well, do you want me to do a best fit line or do you want me to connect the dots? And I'm always saying, do whatever would be best for what you want to get out of the data.
Yes.
So I'd like to do this because when they try to connect the dots, their heads are going to explode.
But you do connect the dots in when you do constellations, but it's just sort of to make a stick figure, not to try and do a.
Would it be possible to get digital copies of these so we could like erase the star data?
Sure.
So that they don't know what we're doing?
Sure. We can. I will gladly give you the Microsoft Word document that we use for this. Okay. And you can adjust and modify it. But our job is to come up with cool ideas, and then your job is to tell us, hey, this is how it can be modified to make it more useful in the classroom. That's how I see this one, at least. Okay? So, yes, if you have ideas on how we can modify this, as I said, this is the second time we've done it. The first time was 2 weeks ago with the previous set of Pennsylvania teachers. So, we are definitely open. And your comment about not starting at 0, was really cool as well. All right, because as an astronomer, I just think very flexible about a constellation is, well, it's just a patch of the sky, so you have to take your box around that patch of the sky. The 0 point is actually irrelevant to an astronomer, right? But recognizing that your kids are really, really focused on that 0 point is an eye-opener for me. So that's good. All right, so if you plotted things the way that I plotted them when I did it in GIMP, you might get something that looks like this. Everybody look up and say, is that what you mostly got?
Yeah.
Yeah, shaking your head, yes. Okay, so this is your plot of Orion. All right, and we can compare that to the photograph of Orion by Tyler Nordgren. And what do we see? You guys plotted backwards? Oh, wait a minute. Oh, wait a minute. There's something I forgot to tell you. Okay, all right. When you're measuring right ascension, there's an important point I forgot. When you're measuring right ascension, the sky rotates from left to right. So when this star passes over and it's 1 a.m., the next star is going to pass over and it's 2 a.m., the next star is going to be passing and it's 3, and that the numbers actually increase from the right to the left. Oh, damn. I'm sorry about that. I forgot to tell you that. So one of the funky things about right ascension is that we're measuring the sky rotating past us. We're not applying our own thing to the sky. Usually everything goes from left to right. So in order to get Orion correct, you actually have to do your x-axis backwards. So this would be the way you truly should label your x-axis. 12, 24, 36, 48, and 6 this way. If you then do the plot that way, you get the constellation as it should appear on the sky. Okay? All right. Now, one of the things that you could go into if you wanted to do some graphing or you want to do some graphical work with this is something that I would call star point scaling. Okay? You'll notice in the table that we gave you something called a column called magnitude. That is the astronomer term for brightness. All right? Magnitude is actually a logarithmic scale. If you need to know the details, I could tell them to you. But basically, 5 magnitudes is a factor of 100 in brightness. Okay? So each magnitude is a factor of 2.512 in brightness, which it's much easier to remember as 5 magnitudes is a factor of 100. But to make things look like the constellations, it actually really helps to scale by magnitude, and this is an optional idea for this. So what I did, oh yes, and this time I will tell you it's an inverted measure, okay? I won't hide that from you. So this is another inverted measure where the brightest magnitude that we're going to deal with today is around 0. The faintest magnitude is around 4. All right? So what I did is I put up a spreadsheet, all right, and I said, okay, magnitude 0 is going to have a diameter of 100 pixels in the plotting program I was using. Magnitude 4 is going to have a diameter of 20 pixels. All right, and I created the little algebra equation in Excel to do that calculation so that Rigel at 0.12 magnitude is at 97.6 pixels, which I rounded to 98 when I plotted it. Betelgeuse is around 90, and Mintaka, the faintest star in Orion, was at 55.4, which I would have rounded to 55 pixels. I then, in my program, I use GIMP, I don't use Photoshop. But GIMP is a freeware version that does a lot of things, same things Photoshop does. So I went in and I made a 55 pixel circle and put it on top of Mintaka, and a 59 pixel circle on Saif, and so on and so forth. Right? In doing that star point scaling, I got this. All right? And I was very pleased at that result. Because that tends to look a little bit more like it. You can see that Betelgeuse and Rigel here have their nice big ones versus some of the smaller ones, especially down here. I guess that's safe there. All right. So that's another optional thing that you can do with this to make it look a little bit more recognizable for the constellations. Okay. I didn't want to ask you guys to try and do that here in class because it really does require using a graphics program to do so. All right. Okay, so now that we have had a first practice with Orion, and we now know that right ascension goes in the opposite direction, let's try a second one. This is the constellation of Leo. All right? So let's see, what can we talk about? In the red shirt, what are the min and max, or give me the minimum of the right ascension for Leo?
Name or number?
Either or both, huh?
9:45.
945, that's Assad Australis.
Right.
Okay, all right. In the black here on the aisle, what is the maximum of the right ascension? The Reagan T-shirt. Isn't that Reagan on there?
Yeah.
Okay.
Ebola.
Danabola is at 1149. Everyone agree with that? So we're going from about 9:45 to 11:49. That's about 2 hours of right ascension that we have to cover. So we'll have to do 2.5 or so. All right, declination. Okay, who haven't we talked to? Have we talked to you about, give me the lowest of the declination. They're all positive.
11:58.
Regulus at 11:58, yeah. Regulus at 11:58 is the smallest declination. And in the gray here, what is the largest declination? Rasalis. Oh yeah, that's a nice name. I like that. Sounds like Rascal or something like that, right? Rasalis at 26. Okay, so we're going from about 12 to about 26, so that's about 14 in declination. We have given you the start chart for Leo, okay, and this one was like 8 by 10 if I remember correctly. Just some stuff I created in GIMP for this, and I will give you the way that I plotted it there, so we all have similar. I will not ask you to do your own axes. You could ask your kid to do the own axes. These guys over here say if you ask your kids to do their own axes, they will go crazy and have a lot of fits. But we all want ours to look the same, so I put the axes up so we can have them the same. Last 2 weeks ago, folks said to me, you know what, it really helps if you put in the numbers along these unlabeled things, right? Because they found just doing this, they got a little messed up. Okay, so recognize that between 10 and 11 is 60 minutes. So this is going to be 15, 30, and 45. 15, 30, and 45. This one's going to be 45 and 30 there. Okay? So they said that will help them. Note that we go by twos on the y-axis, 11, 13, 15, 17, and so forth. All right, please go ahead and plot Leo.
how precise do the directions need to be in the question?
Or even if it.
I sort of leave that up to the teachers. You guys know how to talk to the kids better, right? In terms of what might work for them, because I'm trying to do large, medium, and small.
Yeah.
If I were thinking, the stickers, you can pick up a big sticker, a medium sticker, a small sticker, right?
Yeah.
And that might work to dress it up. Like constellation looks like.
Right.
I was trying to get Excel to do it. Because I put all in Excel.
This is one of the things we discussed at the end of the lecture. Okay, now how might you adapt it for your students? Okay, but that's, you're going there already.
Did you get it?
No, I'm going to, but I'm going to, It's running both the right assumption.
Okay, it looks like most everybody's done with this. All right, if you plotted them the way I plotted them in GIMP, you should get something like this. Does your plot roughly match what I have up here? The head's shaking yes. Okay. All right, of course then we can add in, I did the same scaling of that 100 to 20 scaling, which we were talking up here. Really hard to instruct kids how to do that, but the idea was maybe if you had stickers of like 3 sizes, small, medium, and large, they might be able to just put stickers on top of them to more match the constellation. So here is what, when you add in the scaling, it looks like. And now let's compare that against the constellation. This is a picture from the sky. And what do we see? How'd we do?
The tail seems a little,
Huh?
that last triangle seems a little.
The triangle here,
Yeah.
it seems a little tweaked. Okay. And what about the question mark over here?
Just a little smash.
Okay. Well, rather than smashed, I would actually say the other thing. It's kind of stretched out. Okay.
Stretched too, it seems a little bit more.
Yeah.
Vertically, it seems a little bit stretched.
It's vertically stretched up and down. Okay, so what did we do wrong?
Well,
How come we, I mean, these are just the coordinates of the sky. This is the actual picture of the sky. Oh, it's the scaling. Oh, right. We gotta figure out the scaling between right ascension and declination. All right, so let's think about that, okay? What is 1 circle in right ascension? 24 hours. What's 1 circle in declination? 24 hours equals 360 degrees. So do the math. 1 hour is equal to how many degrees? All right, the answer is 15. You know, I know it's early in the morning. Okay, all right. 1 hour is 15 degrees. Let's take a look at this. 1 hour on our right ascension here is how many? 1, 2, 3, 4 blocks is 1 hour. And 4 blocks, 1, 2, 3, 4 is how many degrees here? 18 degrees. Uh-oh. 8 degrees, sorry. I'm sorry, not 18. 8 degrees. So that's 8 degrees when it should be 15 degrees. I knew there was something I was forgetting. All right, so this is what we just talked through, that the scaling between right ascension and declination has to be correct, right? In order to reproduce what you see in the sky, you have to recognize that you're not measuring the same thing on the x-axis as you're measuring on the y-axis. How you label your axes is actually pretty important in astronomy in order to get things right. So, Orion was actually scaled properly. Yes, I cheated, I set it up just this way. All right, where 1 hour is 5 units, and 5 units here, 1, 2, 3, 4, 5, was from minus 12 to 3, which was 15 degrees. So, it turned out very nicely that I could set up Orion so that it would be backwards, but not scaled, but scaled properly. Leo, when we did it, you can see that we scaled that wrong. So the scale here is a factor of 2 too large and has to be shrunken down. So if you take Leo and instead you adjust the vertical axis to start at 4 and go up to 34, so it's now 15 degrees between here and 19, and 15 degrees between 19 and 34. Notice that I kept the 19 the same, so that I just elongated the axes so they are correct. All right. If you then plot it, you get that. Now, when you compare that against what we see in the night sky, you have a much better approximation of what you see in the night sky. Are we happy with that?
Could you go back to the slide with the scale?
Sure. Where?
The one that defined what the scale should be.
Okay, sorry. Went through that quickly because I talked it out. Sorry. There?
Yeah.
Okay. So, 24 hours of RA equals 360 degrees of declination. 1 hour of RA is therefore 15 degrees of declination. Make sense? Okay. All right, so now that we have gotten our orientation correctly, and now that we've got our scaling correctly, let's do one final constellation, okay? All right, so we've got Leo looking the way it should. By the way, if you are the perfectionist type who hates having a paper that's got a wrong answer on it, and you want to replot these things yourselves, we're happy to give you multiple copies of this so you can replot them. I was worried that people would be like, oh my God, you forced me to plot it wrong. I need to have the right thing, okay? But what is this one? All right, so let's go to the Big Dipper. All right, the Big Dipper is not a constellation, okay? It is an asterism. It is a star pattern that's part of a constellation. What constellation is it? Ursa Major, the Great Bear. All right, and when we look at the Big Dipper, we've got that big long tail on the Great Bear. Do bears have big long tails? They do what?
I said they do when they were flung into the stars.
They do when they're flung into the stars, okay? If you actually look at a bear, do you see a big long tail on Yogi Bear? No, you do not, okay? But if you throw Yogi Bear into the sky, obviously he develops these big long tails because both Ursa Major and Ursa Minor are depicted in the sky as having big long tails. It's one of these silly things in astronomy that we go, hey, it's tradition. All right? So here we have our Big Dipper data. The Big Dipper is, we're using Orion, we're using the Big Dipper, which are the two best known constellation star patterns in the sky. Leo I love because it's a nice springtime constellation, and I love being able to see the backward question mark. Okay, so I tried to choose the most recognizable ones for at least for Northern Hemisphere viewers. Okay, all right. So Big Dipper data. Let's just go through it. Who haven't we talked to? Here in the white sweater, can you give me the minimum of the right ascension? Merak, M-E-R-A-K, 110150. I agree with that. Okay, and over here in the green, what's the maximum? Alki. That sounds like Rolaids or something like that. Okay, Alkade. It's good for what ails you. 1347.23. All right, so we are going from 11 to 1347, a little less than 3 hours, right? That makes sense in RA? Okay, so we've got a little bigger spread than we did with Leo. All right, declination. Who have we talked to in the orange over here? Declination. What's the minimum declination? Alkade again. Okay, Alkade again at plus 49, 18. So we're going from 49. I think we talked to everybody. How about you? Because I just happened to catch your eye. What's the maximum declination?
I don't know how to pronounce it.
Doobie-doobie-doo. Okay, 6145. Could be Dubney. I really don't know. I'm not a specialist.
Kids like Doobie.
Kids like Doobie?
Yeah, they say kids like Doobie.
Okay, all right. So you got a bunch of them. We can have a bunch. We can have the Doobie brothers here. All right. So 61, 49 to 61. What's that? That's 12 or so in declination, right? 12 degrees in declination. All right. So we're going to give you that same 8 by 10 plot for the Big Dipper, and again, I'm going to give you some coordinates. Now, note that I didn't lie to you this time. Okay. There are 3 blocks here, which is 1 hour. It's 5 for each block here, so 1, 2, 3 gives you 15. A 3 by 3 gives 1 hour, 15 minutes. Okay? I didn't lie to you. I put it in the correct orientation and there. Okay? So let's do the Big Dipper. If you would like to remember that we're breaking these up into thirds. The hours are broken into thirds. What's 1/3 of an hour?
20 minutes.
20 minutes, 40 minutes, 20 minutes, 40 minutes, 20 minutes, 40 minutes. Okay? And these are every 5, so you can add in the 40 and the 50 and so on and so forth. Okay? All right. Let's chart that Big Dipper.
Smiling. We're happy. We're connecting the dots. Here. Right. Like this. Got 7.
All right. So it looks like just about everybody's done. All right. So take this. Whoops, got to turn this on. All right. Take all that data, plot that up there. What did I get? I got something like that. Does your plot look something like my plot? Okay. All right. Again, if you add in the brightnesses, there's not a ton of brightness contrast in the Big Dipper. Add in the brightnesses and you get this. Oh, by the way, this star here, Mizar, is actually a double star. It's a visual double, Mizar and Alcor. The middle star of the handle of the Big Dipper. You should be able, there are a couple arc units away from each other. So if your eyesight is good, a way to tell if your eyesight is getting old and really blurry is if you can't separate Mizar and Alcor, then you definitely are, you're getting old and you need glasses. Okay? That's just, or at least your distance vision. Okay? I can't separate things near. That 6-point font they put on the medicine bottles is totally blows my eyes these days, and it's just such an indication of age. All right, so if we compare that against the night sky, what do we see? Did we get it right? Mostly. What's wrong?
It's like buckets belonging.
A little bunched. The stars are too close together. Yeah. Now, in which direction?
In the up down.
In the up down, the sort of scrunched. Well, wait a minute. Leo was actually too large in that up down direction. You're telling me you scrunched up the Big Dipper? I give you Orion and you plot it backwards. I give you Leo and it's stretched out. I give you the Big Dipper and it's scrunched. What are you guys doing wrong? Okay, let's take a look at this. What we're talking about here is the fact that we are not plotting a plane, right? We are plotting a plane that's on a three-dimensional surface. Now, let's think about those three-dimensional coordinates. This is our declination lines, okay? They run from top to bottom. All right? All right, but our longitude would run east-west. All right? Every circle drawn on this sphere is the same size, right? Now, when we look at latitude going up and down, we have the circles going across here, and is every circle the same size? No. The one at the equator is larger than the ones near the poles. The size of the circle changes, and what trigonometric function does it change according to? Anybody know? It's not something I'm expecting you to know. All right, if it starts at 1 here at 0 degrees, and it goes to 0 at 90 degrees, the trigonometric function that starts at 1 and drops to 0 at 90 degrees is the cosine function, yes. So the size of this circle goes as the cosine of the declination, right? The size of these circles goes as the cosine of the declination. Therefore, our scaling between right ascension and declination will also have to have a cosine factor into it, right? Because this scaling never changes, this scaling does change. So when we did our scaling, I forgot to tell you, I'm sorry, I'm just very forgetful this morning, that the scaling is proportional to the cosine of the declination. The right ascension value is 15 times the cosine of the declination in degrees. Okay? Now you're telling me, well, wait a minute, it worked for the other plots. Why would it have worked for the other plots? Well, because I sort of set it up that way, okay? Let me show you. For Orion, the central declination on this plot is -1.5 degrees. The cosine of -1.5 degrees is 0.9997. So when you take a plot around the equator, well, that 15-degree scaling is roughly accurate, okay? The deviation is down in the second and third and fourth decimal place. So you're going to get this one right. For Leo, the central declination is 19 degrees, all right? The cosine of 19 degrees is still not that large, not that different from 1. It's 9.455. So there is an error in this, but it's on order 5% or so. Okay? As you get further away, the error will be more in this direction and less in this direction. So the scaling of 15 is roughly accurate to 5%. Could we actually see 5% with our eyes here? Not really, okay? You could probably do a 10 or 15% error. But when we go to Ursa Major, all right, and the Big Dipper, the central declination here is 55 degrees. Okay, that's well up in the northern part of the sky. Okay, that's why it's a constellation that these two stars point toward the North Star, right? These are the pointer stars that go up, and Polaris is up here. Here, the cosine of 55 degrees is 0.5736. So the error is of over 40%. Can we notice an error of 40%? Yes, we can notice an error of 40%. Even your students should be able to notice an error of 40%. So what we need to do is actually rescale the plot here according to if we take that cosine and add that into our scaling. So we take a scaling of 15 times 0.6, which would be about 9, all right? So instead of 1 hour equaling 15 degrees, it should go the other way, right? No. A 1 hour RA is, yes, 15 times the cosine, so 15 times 0.6. All right, we did this, it's going to be around 9. Rescale this, and what you need is, from the top to bottom, keeping 55 in the center, your bottom at 43.5, your top at 66.5. Doesn't work out in nice even numbers. It doesn't always do that in science. And then you plot it. Okay, oh, sorry. That should have come before. Why didn't I? All right, so here, central cosine around 0.57, 8.5. Okay, I was doing it in my head and I got 9. All right, so this 8 times 4 over 3 is 11.4. So I made it 11.5 here. Okay, and then got this scaling. All right. If you need to know the math, we can discuss it. But basically, in doing the scaling correctly, we can see that we have this, and we get a Big Dipper plot that looks like our picture on the sky. All right? So, I forced you guys to make errors. All right? And hopefully, in that way, we taught you about the funkiness of the astronomical coordinates. Recognition that you are not only plotting something in unusual coordinates, the right ascension is backwards, that there is a specific scaling between the coordinates, and that scaling, because you're really looking at spherical coordinates and not planar coordinates, that the scaling changes across the sky for that. All right? So it seems easy to do this constellation plotting, okay? When the first idea comes up, oh yeah, you just plot the stars. And then as we developed this exercise, it was like, oh wait a minute, it's not quite so straightforward. There are some idiosyncrasies to it. And you're doing spherical coordinates in practice. Instead of starting with spherical coordinates and knowing that you're doing it and then understanding it by making mistakes. And people say that one can often learn more from mistakes than by doing things right. I like to think that sometimes too, but at least we give you the answers so you can do it right in future things. All right? So if you wanted to do advanced star plotting, there is more data that we gave you. We gave you the position on the sky with the RA deck. We gave you the magnitude and luminosity. I showed you how you could use the magnitude. There's also the spectral type, which indicates the color and temperature. If you wanted to get lots of little colored dots, and so that Betelgeuse really looked a little bit orangish yellow, and then Rigel really looked that little bluish thing, you could do that for colors. You can also do distance, which I will discuss tomorrow when we're doing our 3D visualization part of our discussion of this week's thing. But we gave you the distance so you could actually, we were talking up here, how that we're taking what is 3 dimensions and we're putting it on a plane. All right, when you put this on a plane, how far away are the stars? They're all at the same distance, right? Of course, that's not true, and you know that, but this creates a misconception in your head by simply putting it on a plane. All right, and we'll discuss how to address that in our discussion tomorrow. All right, and I think there's one more. Oh, okay, we'll get to that in a second. So, yeah.
With the spectral type, you said that goes with the color.
Yes.
Is there any sort of key for that?
There is a key for that I can give you. It's not a straightforward key, unfortunately. In order, I'll show you but basically we have, what did we give you spectral type in? Yeah, we gave you in the OBFGKM. I showed you the other day the OBFGKM color things. That is really, there's no, I can't say RGB equal, I can't give you an equation to go from spectral type to RGB numbers. You end up using a bunch of lookup tables for that. Okay. Now over here, you were trying to do something in Excel. Tell the class about what you were trying to do.
I was trying to plot it.
Okay.
Still putting in his times. It let me enter them in as long as when they were negatives, it threw a fit.
Oh, okay.
And so I couldn't do the first one, but the second one was able to do it. But then, being the helpful computer that it was, it kept trying to adjust my axes for me, and it really didn't. It was tough. I had to figure out monkey with the decimal value that the time actually represented to get it to. It wasn't cut and dry, something you could show the kids or anything. So just stick with the paper and thank for plotting out for the students. They really have to be pretty advanced to go through how to set up the axes on Excel, and because it kept trying to set the axes for me and it wasn't going well.
Oh, okay.
It took a lot to get it to kind of pull the graph out, the XY plot, so it actually looked like Leo.
Okay, cool. All right, because we had a tech ed teacher here 2 weeks ago, and he said that part of what he does is, he said he thought this would be interesting to try in Excel because what he's looking for is cool stuff to use in Excel. In order, he's trying to teach them Excel and details of it. And he said, well, maybe I'll try this in Excel, see if I can do it now. You've just done the experiment.
Yeah, if you converted the time-based value into a decimal, it probably would fly.
Right. In truth, when astronomers do all this, we have a standard function we call. It says, here's here's hours, minutes, seconds. Give me a decimal. All right, we convert it to 360 degrees in RA. Okay, that's how we truly plot it. So that's when we do our plotting functions. We keep with the astronomical coordinates because those are traditional, but we convert them to what's easier to plot.
Yeah.
So you are correct. We do that. Converting from 24 hours to 360 degrees is probably necessary before Excel will start to handle it.
Yeah, it's kind of what I figured, especially with those negative values.
Right, so really that's actually probably the way that we'll suggest if people want to try it in Excel, is go from hours, minutes, seconds to degrees, minutes, seconds first, and then you have common data to then work for the plot, and Excel won't try and readjust it too badly. Okay, cool. All right, but then we'll have to worry about the declination scaling as well. Right, figure out some sort of declination scaling for the average for the plot. Okay, that's good. Other comments on how this might be used in the classroom or improvements or other things. You noted that some students are, when you teach plotting, they have the 0, 0 point, and that's where they work off of. As you can see in astronomy, we don't really think about that too much. Is there a way, you think, to get them to recognize these more general idea of the labeling of the axes, or just give it to them?
Well, now I'm thinking it might be, I have this thing that projects constellations onto the ceiling.
Yeah.
And I think maybe if I could figure out some way to get a grid up there, I could probably get them more the idea, okay, here's your piece of paper and you were grabbing this part of the grid.
Okay.
Not, if you were grabbing 0, 0, you'd be somewhere else.
Right.
As opposed to just, here's your flat piece of paper and this is how we're going to graph, and it's the same kind of graph you do in math.
Okay.
Because it's not the same kind of graph you do in math.
Okay. No, it isn't. This is trying to expand their ideas, give them something unusual. A lot. Yeah. All right. By the way, do you know where the 0 point is on the sky?
0, oh, like 0, 0?
Yes, 0, 0. Do you know what the 0 point is on the sky? Okay, it's the position on the sky where the sun crosses the ecliptic plane on the vernal equinox. Okay? So every spring, wherever the sun is at the vernal equinox, that's the 0, 0, that's the 0 point in the sky for right ascension. Okay? That's the 0, 0 point. Now, that's the traditional 0, 0 point. In modern coordinates, we can use very distant pulsars and quasars and other things to set our coordinate system. So because Earth's rotation and other things, that coordinate system will actually shift over the course of 1,000 years. The coordinates that Ptolemy put into his book 2,000 years ago are wrong for today's coordinate system because Earth has wobbled a bit, and therefore the coordinates of all the stars change over time. So one of the funky things is when I give you an RA in a deck, all right, I actually have to tell you at what time in history that they were recorded at. These coordinates are J2000 coordinates, giving the position of the sun based upon the position of the sun on the vernal equinox in the year 2000. We have generally gone from 1950 coordinates to 2000 coordinates. We're probably going to stop at the 2000 coordinates and never change them again, simply because we can define things relative to very distant objects. We don't have to use the stars anymore to define our coordinates. So I'm not sure we'll ever use 2050 coordinates. That will all stop at the J2000 coordinates. And the FK5 system is what it's called, that uses the J2000 coordinates as their basis. That may be what we use for the rest of history. But that's a little bit of a side note on that. All right, cool. We went along with that, John, just like we did last time. But I think it's a fun exercise. I hope you guys enjoyed it. All right, let's take our 15-minute break, and we'll come back and start on extrasolar planets.
Really cool.